Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to our lecture. Today, I'm going to start chapter 6, periodic properties. It's continuation of, looking at the elements on the periodic table. Some of the concept we learned in previous chapters, chapter 5, chapter 6, we will use in chapter 7, more so the writing electron configuration of element. As usual, there will be two parts, part A and part B. Part A, section 7.1 through section 7.4, and from section 7.5 all the way, the rest will be part B. I will share my screen so that you can look at the whiteboard and the lecture PowerPoint slides. Please have a paper or a notebook so that you'll be taking notes. As usual, I will break down the title of the chapter, right? Periodic properties of elements. When say elements, this refers to the elements on the periodic table. You know the periodic table. Previously, we looked at the elements, classifying them as metals, non-metals, or metalloids. And groups and periods, those are something you should know. Now, property here, strictly property is a characteristic feature used to describe an object. It turns out that periodic table, right? Periodic table is a powerful tool which enables us to understand physical properties of element. When we say physical, this refers to either the color or the trend in densities of element on the periodic table. It could be also the color, okay? Chemical properties also, this has to do with how element in a particular column, in a particular group, or react with other elements to form a compound. There will be a pattern, you'll see that, and this has to do with the recurring patterns of electron configuration. The recurring pattern for those physical and chemical properties has to do with the electron configuration. In chapter 6, we learn how to write the electron configuration of element in ground state. Please revisit again, make sure that you are in a position to write electron configuration. Previously, we learned that element in one column react the same way. It's because of what? It's because of electron configuration. Electron configuration. Now, chapter 7, periodic properties. Okay, explore the fundamental characteristics of all elements. Characteristics of elements. I said there will be two parts. Part A, section 7.1 to 7.4, we look at the development of the periodic table, how we ended up with the periodic table. Initially, it wasn't the way it looked like at the moment, but different scientists had to work on it, on organizing the modern periodic table. We'll see the development, how it was invented, how the elements were arranged. The concept of nuclear charge, which gives rise to the chemical as well as physical properties. And we look at the definition of the radius, atomic radius, and how the trend on the periodic table changes for both what? Neutral atoms as well as ions. Remember, ions these are charged particles. And then lastly, in 7.4, we look at the ionization energy. That's the energy required to remove an electron from an atom or ion in its gaseous state. Part P, we will pick up from 7.5 electron affinity, which is the energy given off when an electron is added into a neutral atom or an ion. Of course, you should be able now to, break down the periodic table as either metals, non-metals, or metalloids, and then trend on some of the group 1A, group 2A element, and lastly, trend of selected few elements, Now, the periodic table, 7.1, periodic table, the way it is right now, this was not the way it was in early 17th century to late 18th century, but initially there were only about 9 known elements to begin with, and chemists didn't, or scientists didn't have any problem maybe memorizing their physical properties and chemical properties. But if you look at the discovery of, early 17th or mid 17th century, several elements were discovered, right? Around 42 elements. And if you add to early 1800 to late around, this is 70 elements added at the same time, which means there was a staggering or taunting effort on keeping track of where things are or which elements react with this. If you want to know which element is in a particular compound, they had to organize the periodic table, and several scientists had to work on that. And right now, on the screen, Dmitry Mendeleev, he was a Russian chemist who organized the periodic table according to increase in the mass of oxide of elements. His periodic table was not the way it is right now, but he was reacting elements, all right, with oxygen to form oxide and weighing them to see the pattern. And stands out that it was following a pattern that oxide, for example, lithium was lighter than the oxide for beryllium and so forth. A German chemist by the name John Lothar Myers was also looking at the periodic table. They arrived at the same conclusion, looking at the elements on the periodic table. However, the modern periodic table, we give credit to Dmitry Mendeleev for organizing or giving rise to the modern periodic table because of what? Because he was able to predict yet undiscovered element at that time. Gallium, for example, he predicted it had not been discovered, but Lothar Myers did not predict anything, even though they came to the same conclusion. But the modern periodic table, we give credit to Dmitry Mendeleev. So here are, this is the main reason why Mendeleev is given credit for organizing the periodic table for germanium and gallium, which means before silicon. Eka-silicones means before silicon. Eka-silicon, germanium, see here, the Mendeleev predicted that the atomic weight will be what? 72, and the actual, when it was discovered in 1876, in 1886, sorry, turns out to be 72.59. All right. Its density 5.5, 5.3. This actually, if you look at these physical properties, they are more or less, exact to say, or precise. It's just close to. That's the main reason why Mendeleev is given credit for organizing the periodic table. So chemists mostly credit Mendeleev because he has also organized the table and predicted some of the missing elements. Germanium is one of them, and we have seen the properties. Other than that, they came to the same conclusion as what? As the German scientist. So remember what? Remember, he organized the periodic table according to increase in masses of oxide. So he was basically organizing the table according to the masses, not atomic number. And how did we end up with the atomic number, which is the position of an element on the periodic table? For example, let me just shift to a periodic table. You look at the periodic table here. This is the periodic table, number 1, number 2, number 3, number 4, number 5, number 6, and so forth. You have seen this before. The modern periodic table is based on the arrangement according to increase in atomic number. And how did we end up with that? Atomic number is the position of elements on the periodic table. I just want to show you the atomic number and how we ended up with that. So remember, before the discovery of atomic number, the periodic table was arranged according to atomic masses. Now, all right, before or in 1913, an English physicist by the name Henry Moseley developed the concept of atomic number experimentally. Before that, Rutherford had proposed the nuclear model of an atom. So what we know is that at this point, let's say Rutherford nuclear model of an atom. Let's have this first. So we have this. He proposed that electrons are outside what? Outside the nucleus. We know in the nucleus we have the protons, which are what? Which are positively charged. This is the nucleus. Nucleus model of an atom. Okay, so now what Moseley did was he developed the concept of atomic experimentally. How did he do that? It's because Mendeleev periodic table, if we arrange the periodic table according to atomic masses, you will find that the metal will be in the non-metal territory and the non-metal will be on the metal territory. And I'm going to show you before I move forward with this experiment that if you look at, let's say, for example, argon and potassium. Argon and potassium. If I look at the atomic mass of argon, it is 39.948, but for potassium it is 39.098, which obviously potassium weighs less, argon weighs more than potassium. So if we take potassium, place it here and then argon here, we will be mixing metals and non-metals. This is not the only, I'm just using this as an illustration. You can also look at what, you can also look at the cobalt and nickel. Cobalt is 58.93 whereas nickel weighs 58.693. It weighs less. So if we copy Mendelev's approach of organizing the periodic table elements, they will be mixed up. So what we need to do is, what we need to do is get the periodic table, or what Mosley did was organizing the table according to atomic number. And what he did was bombarding the nucleus, bombarding the nucleus with positively charged particles. So here is positively charged what? Positively charged particle. And in this case, in case of potassium and argon, we count the number of positive charges in potassium, it turns out to be 19, which is 19 protons for neutral potassium. For the nucleus of argon, we have 18. So 18s can be for 19. So understand that Mosley developed that by bombarding the nucleus of each element and counting the number of positive charges. And the number of protons here was considered to be the basis for the periodic property of elements increasing. And therefore, this modern periodic table is based on increase in atomic number, which we know atomic number is basically the number of protons, right? So 1 proton, 2 protons. We know rubidium has 37 protons and so forth. So that's how the atomic, all right, that's how atomic numbers, all right, that's how atomic number was developed by Henry Moseley. Now, this is a typical question you will encounter either in a quiz or exam does. So you need to know the contribution of each of these scientists. Henry Moseley is credited for developing atomic number. The correct answer for that is A. Lothar Myers, you will only see being mentioned. It's just being mentioned. They don't give him credit, even though he came to the same conclusion as Dmitry Mendeleev, but because he didn't predict yet undiscovered element at that time, he is not given the credit. Now, Michael Faraday, I think this is physics, so we're not gonna get into that. Ernest Rutherford is credited for the nuclear model of an atom. We talked about this previously. Now, periodicity is simply the repetitive pattern of property for element based on atomic number. That means there is a recurring pattern. Remember, a property is a characteristic feature used to describe. So when we talk about periodicity, that means after a certain period, you see again a recurring pattern. And in chapter 7, here are the repeating pattern we will look at in details in chapter 7. Atomic sizes of atoms and ions, and remember ions are charged particles, either negative or what, or positive. We're gonna talk about the cations or anions. We will look at the ionization energy. I'm going to define that, okay, as explained earlier on. It is the amount of energy required to remove an electron in its gaseous, an electron from an atom in its gaseous state, from an atom or ion in its gaseous state. Now, electron affinity is simply the energy given off when an electron is added into a neutral atom or ion in gaseous state, and some of the chemical properties we will see the trend. But first, let's look at fundamental property that leads to many of the trends. Here should be many of the trends, and this is the effective nuclear charge. All right, effective nuclear charge, which I'm going to define, all right, for you so that you understand what this charge is all about. Okay, hope you are writing your own notes. So this is effective nuclear charge. Effective nuclear. Effective nuclear charge. This is the actual, right? Actual, or rather here, we're gonna have this. This is the actual, I wanted to say actual amount of nuclear positive. This is amount of positive charge in multi-electron atom. That means with more than one what? More than one electron. Hydrogen one electron, but we're talking about multi-electron. And it's just gonna have this a little bit here, so that you look at that. Multi-electron atom. This is attractive, or simply attractive, positive charge. Okay, nuclear protons. You know, in the nucleus we have the proton. In the nucleus we have the protons acting on valence acting on electrons. So here is simply the definition of the effective nuclear charge is actual amount of positive charge acting on the valence electron. Okay, so let's say in sodium we have 11 protons in the nucleus, and if we write the electron configuration for sodium, we have 2 electrons, 6 electrons, all right, that give you 8. Sodium is number 11. So these are 2, 1, 2, 3, 4. We have 8, 10, and then we have 1 electron. This is number 11. Sodium is number 11. It has 11 protons. So effective nuclear charge here is simply the charge experienced by this valence electron. Electrons are negatively charged, protons are positively charged, and what happened here is there will be force of attraction acting between the nucleus and the valence electron. This is the valence electrons. So understand from the previous chapter what we mean by the valence electron. The nuclear charge here is the charge or the number of protons. I use here sodium, which is number 11. If it is neon number 10, it's going to be 10 protons. If it is hydrogen, 1 proton. If it is helium, 2 protons. If it is magnesium, 12 protons, and so forth. So the nuclear charge here varies from element to element to element. Now, we will look at how to calculate the nuclear charge, but for multi-electron system, many properties depend on the attraction between the valence electron and the nucleus. So here is the nucleus, and I've used sodium, where we have sodium, or rather, just blow this up so that you see that there is, or we have 11 protons, and there is 1 valence electron in the 3s sub level. Okay, 3s sub level. Electrons are both attracted, all right? Electrons are both attracted to the nucleus. It's just going to be attracted to this and repel each other because of what? They are negatively charged. They tend to repel one another because they are negatively charged, negative and negative to repel. Now, the forces acting on an electron, the forces acting on that single electron are influenced by both factors, that is repulsion between electrons and the force of attraction between the protons in the nucleus and that electron, or rather the valence electron. There is a pattern here, trend on the effective nuclear charge. But before we look at that, here is the equation I may give you in the exam. All right, please practice on how to use these equations. Z effective is effective nuclear charge. C subscript E is basically effective nuclear charge, and it's obtained by taking the atomic number minus the screening constant, which is basically the number of inner electrons. What does this mean? For example, here, let's just minimize this. I use my whiteboard. For example, here, okay, for example, if I have this neon, all right, which is Na number 10, it has 10 electrons. C effective, or rather, let's say magnesium. I mean, just use magnesium. I don't want to use that. I'm going to use magnesium as an example. Mg, which is what? Which has 12 protons. It has 12 protons. In this case, Z effective is given by the atomic number, which is 12, minus the S here is 12, or I mean 10 electrons, the inner electron. So here, minus 10 equals positive 2. This is the S, or shielding electrons. It's just shielding electrons. So the core electrons, all right, closer to the nucleus is the screening constant. Usually they're close to the number of inner electrons. That's how you start. And I want us to look at the trend here on effective nuclear charge moving from left to right. We see that it's increasing. All right, charge of the nucleus is increasing. This is just the atomic number. You look at C effective, this is atomic number. C effective increases according to increase in atomic number. I'll not look in details on how these change. That is C effective for valence calculated with equation 1. All right. If you look at number 10, after number 10, it drops significantly because of what? Because of the shielding electron. Because of this shielding, the effective C effectives drop drastically because of the shielding effect for core electron, and then start picking up or increasing as we go along. So take note of these bullet points that are generally C effective is a periodic property which increases according or going across the periodic table from left to right. You see in the multiple choice, how does the trend on C effective changes or effective nuclear charge? It increases slightly down, but not that much. It increases, but not that much. Here is an example on learning, on an example on a quiz or exam, learning check. I call it learning check. See if you have learned something. The greatest effective nuclear charge in many or multi-electron atom is experienced by an atom in a dash subshell. Remember, the C effective, let me just minimize this. C effective is simply a function of how close it is to the nucleus. And if you go away from the nucleus, there will be more shielding, moving from energy level 1, energy level 2, energy level 3. And here is the greatest, which means the closer to the nucleus, the greater the C effective. And in this case, our answer is A. 6S will be the least. 6S will be the least. I don't want you to get confused with that. Please always underline and highlight what the question is about. So here, greatest effective nuclear charge. That means strongest force of attraction between the electron in that subshell or in that shell with the nucleus, and 2s is closer to the nucleus. In thin, which is number 50, electrons in the subshell experience the lowest effective nuclear charge, which means as you go away from the nucleus. I'll expect this to be 5B. All right, if you write 5B, this is the strongest or the highest. The greatest is 1S, but here 5B, D is the correct answer. That's all what I want to cover in C effective or effective nuclear charge. You should know the trend on the periodic table. You should be able to calculate the effective nuclear charge using the equation C effective equals to atomic number minus S, which is, this is number of what? Shielding electrons, number of shielding electrons, or core electrons, That's what you need to find. And this is what? This is the effective nuclear charge. Effective nuclear charge for experienced by valence electron in an atom. Before we look at the trend on atomic sizes, all right, atomic sizes, let's look at the definition of bonding atomic radius and non-bonding atomic radius. Non-bonding atomic radius. The bonding atomic radius between the nuclei of two atoms Non-Poynting atomic radius or van der Waals is half the shortest distance separating the two. So here, if you look at the distance separating the two, a half of it is the Poynting atomic radius. A half of this D is the bonding. You have this, but this is just non-Poynting radius. This is always shorter than what? The non-Poynting. Poynting atomic radius or covalent radius is half the distance between the two nuclei. It's just, you should be able to define those terms. All right, you can write on that. Now, there is a pattern on the trend on atomic sizes and ions. Remember, ions are positively charged. And as you go along, this is what I'll recommend how you can keep track of or commit to your memory the change in atomic sizes. I'll say this is my periodic table. All right, here is atomic radius or atomic sizes. Yeah, atomic radius decrease as you go from left to right on the periodic table, and this is increase as you go down the periodic table. All right, so as you go down the periodic table, if you look at this, it's increasing as you go down the periodic table. If you are moving from left to right, it decreased. Did I say increase? Let me just say, yeah, it decreased. But if you move from left to right, it's increased. You have to know which direction you are pointing. Mine pointing left, decrease. But if I'm looking at this direction, it increase. Those are some of the terms you may see in multiple choice, but nevertheless, you need to understand that moving from left to right decrease because of what C effective. Why is C effective increasing? What this means, or the reason why we see this pattern, is if I'm going from left to right, it's like this. If you look at what is happening, it's the same size, all right? Because you are not increasing the shell when you are adding the electrons, it's going to be on the same shell, whereas the nuclear charge keeps on increasing. For example, in an atom of hydrogen, there is one electron in 1s. For helium, 2 electrons in 1s, which means we are adding electrons to the same sub-shell, whereas the atomic nucleus increase from hydrogen to helium, which means the valence electron in helium will feel the force or create a force of attraction between the proton in the nucleus, and that valence electron, therefore, is going to shrink. So force of attraction gets stronger as the number of proton in the nucleus increase, and we are adding the same, we are adding electron to the same shell. We are not changing from. So that is meant by C effective going up because of the number of protons. So C effective goes up because of increase in what? Because of increase in number of protons or nuclear charge. That's what is causing this pattern. That's what is causing this trend. Now it increases from top to bottom. Why? The reason why that happened is this is what's happening. We are increasing the shell You see the shells? As you go down a group, it increase. This is a trend on atomic radius, trend on atomic radius. So you're gonna have that. You look at that atomic radius. As you go, we are increasing n number. That means n here, n equals to recall principle, energy level, or shell what? Shell number. Remember shell number 1, shell number 2, shell number 3. As the number of layers get bigger and bigger, the size of the atom also increase. Well, you may see a general question on the trend, but you may be given a periodic table and you are asked to arrange element according to increase in atomic radius, decrease in atomic radius, or you may be asked which one of the following has the least atomic radius the most. But with that understanding, this trend, we can conclude that barium has large atomic radius compared to magnesium. It increases going down a group, it decreases going across, and you can use that to answer any question on atomic radius. Here is an example on trend on atomic radius. Okay, all right, which part of the periodic table, top, bottom, left, right, has the element with the largest atomic radius? It is, all right, bottom left on the periodic table. It's a concept you need to know. In the exam, you'll just be given the regular periodic table, and a question such as one you see on the screen, of the following, which gives the correct order for atomic radius for magnesium, sodium, phosphorus, silicon, and argon? Which gives the correct order? That means from the least, all right, to the greatest. You can use elimination method here, that argon is on the far right, which should have the what? The least or the smallest. And remember, this means crater. By the way, if you didn't know, this means crater in Mars. This means crater. And this means less, right? So when we have this, it means argon is greater than. No, argon cannot be greater than, should be the least. So if I use elimination method, argon should be the least, and this should be, all right, we should cancel out A and C, because of what? Phosphorus or argon cannot be less than, so A, P, C will go. If I look at sodium being greater than magnesium, silicon, the correct answer is D. The correct answer is D. How you come up to conclusion is, if you have this, if I look at this, sodium, magnesium, this one is larger than magnesium. Then if you look at silicon, phosphorus, and argon, this should be the least. That should be the least. What that means, our final answer is D as in David. D as in David, all right. just an example on how you may be asked a question on the trend in atomic radius, not necessarily that you must be given the actual numbers, all right? But by just eyeballing and using the understanding on the general trend, you should be able to answer question on atomic radius. Now, let's see the sizes of ions. Remember ions, all right? We defined these earlier on. Ions are charged particles. These are charged particles, and it can be what? These can be cations, can be anions. We're not going to look at the polyatomic ion this time, but you should be aware that we have cations, anions, we have polyatomic cations, polyatomic anions. This includes sightings as chloride or fluoride. They are negatively charged. These are positively charged. You should know how these ions are formed. Metals generally tend to lose. So let's look at the sizes. How does the change in or trend in ions for group 1, if you look at the size of ion in comparison to parent atom, they are always small. That is one thing you need to know as far as cations are concerned. All right. Cations are generally smaller in size compared to their parent atom. This is parent atom, this is parent atom for sodium cation, for potassium cation, and so forth. For anions, they are always larger than the parent atom. This is chlorine, all right, sulfide, oxide, fluoride, chlorides, selenite, bromide, telluride, iodide. These are what? The trend in anions. Anions are generally larger in radius compared to their parent atoms. The ionic sizes, just the radius, depends on one, the nuclear charge, all right? It affects the number of electrons. If you look at the number of electrons, if we remove an electron, what causes this, if we remove an electron from a parent atom, the nuclear charge will keep constant, still gonna be the same, but we have less number of electrons, which means there will be more electron, there will be more nuclear charge, there will be strong nuclear charge pulling those remaining electrons towards the nucleus, therefore shrinking the size of cation. Likewise, for adding electrons, the nucleus will be overpowered by extra negatively charged particle. There's an electron making it larger. So cations are smaller than their parent atoms. So just explain, the outermost electron is removed and repulsion between electrons are reduced. So if we remove that, it will reduce the repulsion. And what happens when we add an electron? Adding electrons or electron to neutral atoms, we end up with anions. And anions are larger than their parent atom because of what? Electrons are added and repulsion between electrons are increased. Repulsion between electrons are increased, making the anion increase. Well, in chapter 6, we looked at species having the same electron configuration or same number of electrons. Those species are said to be electronic series. So in an electronic series or isoelectronic series, sorry, of ions have the same number of electrons. That means we have the same number of electrons. What determines the size is there is decrease with increase in the nuclear charge. So if I have for isoelectronic, this is nuclear charge. Atomic radius. So if you look at the nuclear charge decreasing, nuclear charge increasing, sorry, nuclear charge increasing, the atomic radius also decrease. And this has to do with the C effective as well. So number of protons keeps on increasing because of the what? The protons, 8, 10, 9, 3 to 13. They have the same number of electrons. We say they are isoelectronic species with the same number of electrons. The point here is for isoelectronic series, the size of the ion decrease with increase in the nuclear charge. Nuclear charge, in the nucleus, we have the protons. Aluminum has 13 protons, magnesium 12 protons, sodium 11, so forth. The size decrease with increase in nuclear charge. Having said that, how do you, all right, how do cations of the same nuclear charge change in radius as you move down a column in the period as you move down a column? Same charge. In a column, it gets larger. It gets larger because if you look at this is the same column, same charge, same column, same charge. It is getting larger and larger. So here, the correct answer is B. You will not be given this table, by the way, will not be given this table, but understand the trend in the nuclear charge. So B. Dash is isoelectronic with krypton. Krypton, you gotta look at the periodic table number, what? 36. So selenium, if I look at selenium, if we look at the selenium, with the I want us to look at selenium. That's not what I want. I want it is to really, yeah, right there. Krypton, I wanted to show you, this is krypton right here. We want something with 36 electrons. Understand the overall negative charge means we have extra electrons. For example, selenium, we have 2 extra electrons. So selenium here is number 34. If we add 2 electrons, it will end up with 36, which is the same as krypton. So A is the correct answer. It is isoelectronic. That means they have the same number of electrons as krypton. Bromine is number 35, and the way it is right now here, we only have 35 electrons. It's not isoelectronic with krypton. Selenium positive 2 means we are less by 2 electrons. That means gonna be like germanium 32. Here we have 32 electrons, and it is isoelectronic with germanium number 32. Selenium 3 3 negative, that means we do it. I was looking at this. Selenium, that means we are at 3, like 1, 2, it's gonna be something else, you know, here, 3 electrons, 1, 2, 3, this is like rubidium number 37. So you have a concept, tellurium, which is right here, adding 2 electrons will be like xenon. This is isoelectronic with xenon number 54. The key thing here is knowing the key term here, isoelectronic. Isoelectronic means same number of electrons, means same number of electrons. In isoelectronic, I guess, isoelectronic, they have the same number of electrons. They should have been either chromium, but nevertheless, which one has the largest? The calcium, the largest, all right. Ionic radius, ionic radius. Well, that is all for atomic radius. Please read more on that. Look at the end of chapter problems on atomic radius and ionic radius. Make your own notes. Let's move on to 7.4. This is the last part on part A. Part P 7.5 will come back again for that. Let's see ionization energy. I defined earlier on ionization energy at the beginning of this session. Ionization energy, you need to commit this to your memory. You should be able to define in an exam or quiz or even peon. We use I, italic I, for ionization energy, and it is the minimum amount of energy required to remove an electron from ground state of gaseous atom or ion. The key thing here is ionization energy. The key thing is ground state of an atom in gaseous. It cannot be solid, cannot be liquid, but it can be gaseous state, and not necessarily a neutral atom. It can be ion. All right, it can be cation, it can be anion. The subscript 1, 2, 3, and italic I, this stands for first ionization energy, second ionization energy, and so forth. That ionization energy, know how to interpret this. First ionization energy is the energy required to remove the first electron. First electron. Let me just illustrate what this means in terms of fast ionization energy. All right, fast ionization energy, it will be sodium going to Ni positive plus 1 electron. This is fast ionization energy. If I remove the electron from this sodium, which is positive, going to Ni 2 positive plus, this is second ionization energy. And then if I have Na2 positive, going to Na 3 positive plus electron, this is I3. So that you understand what the fast ionization energy, that ionization energy means. That ionization energy means. This is fast ionization energy. second ionization energy, and that ionization energy. This one will require some energy. This one will be more difficult. This one will be even the most difficult. The more it gets positive, the more it's difficult to remove an electron. So second ionization energy is that energy required to remove the second electron. And remember, we do not remove two electrons at one shot or one pull, one remove. No, it's always one electron, one electron, one electron. So when you talk about fast ionization or second or fourth ionization energy, you remove the first one, the second one, the third one, and then the fourth one. Know that the higher ionization energy, the more it is difficult to remove. All right. Here is the trend on ionization energy: fast ionization energy, second ionization energy, all the way to seven ionization energy for just few elements on the periodic table. Please look at table 7.2. It's in the text. All right. What this means is, look at bullet point number 1. With respect to ionization, it requires more energy to remove successive electrons. So if we remove for sodium, fast ionization, look at this, from 496 to 4,562 successives. All right, it's because we are removing the core electron. Look at this, magnesium has 2 valence electrons. If we remove the first electron in its 2 valence electrons, 738 kilojoules per mole. Second ionization energy, 1,451. But look at the third ionization energy, because we are removing the inner shell electron or core electrons. Inner shell or core electrons. All right, inner shell or core electrons, making it difficult to remove those electrons. When all valence electrons, electrons in the outermost shell have been removed, it takes a great deal of more energy to remove the next electron, or in this case, core electron. So here, this gray shaded area represent removal of core electrons, which is why we have high or more energy to remove those electrons, Let's see, periodic trend in the fast ionization energy. What we learn or take home from fast ionization energy is this. Point number 1, generally it increases across a period. As you go across the periodic table, fast ionization energy increases. As you go down, it decreases across. So if I want to see the general trend, not necessarily memorizing the bullet points right there, here is fast ionization energy, or I like that, and then 1, as you go across like this, generally increases across. So we'll say increases right here. This is periodic table, assuming that we have the periodic table, and then decrease. The reason why I want you to understand this as your periodic table, the reason why I'm bringing this is you may be given a multiple choice question of element on the periodic table, and you are asked which one of the following will have high fast ionization energy, low or lowest ionization energy, or arrange the following according to increase in fast ionization energy. It will be a function of understanding the trend on the periodic table. Then you just have to eyeball. Remember the blocks of element S and p-block elements show a larger range of fast ionization energy, whereas the d-block generally increases slowly across the f-block elements slowly only available. Please just note those 3 bullet points. Factors affecting ionization energy. Why do we see that trend? Smaller atoms have large fast ionization energy. It's because of the C effective, which we looked at previously in section 7.2. We also look at how to calculate the C effective. And the trend we are looking here has to do with the nuclear charge and the average distance of electron from the nucleus. The farther it is away from the nucleus, that means the electron in the nucleus will not be in a position to do what? To pull those valence electrons towards the nucleus. It's going to be very easy to remove the electrons. Oh, well, we talk about the ionization. It increases as you go from left to right, because the size of the nucleus, the size of the radius gets smaller and smaller. The size of the radius gets smaller and smaller. It's going to be very difficult to remove that. Here is an example on exercise 7.3 in the text trend in ionization energy. We have 3 elements, the red, the blue, and the green. 3 elements are indicated in the periodic table in the margin. Which one has the largest second ionization energy? All right. You don't know which elements are those, but based on the periods and the rows, this is group 1, this is group 2, this is group 6A, group 1A, 2A. So if we are removing the fast ionization energy, that means we are done with the 1 valence electron, and the next one will be core electron. Remember what we said about the core electron right here, right here. If you remove the fast electron, you remove the core electron, it's going to be very difficult to remove that core electron. And in this case, sodium, even though I may not be in a position to tell whether this is sodium or any other element, the fact that it is in group 1, I know they have only 1 valence electron, and if I remove in the fast ionization energy, second ionization energy will be the core electron. And here, largest second ionization. Second ionization energy means removing the second electron after removing the fast electron for fast ionization. So sodium is the correct answer. The red box right here, it is critical thinking. It's a conceptual question. You don't know which element is that, and if you don't do your groundwork well, you'll just be left guessing and say, oh, I need to be given the element name, I need to be given the atomic number. It's just a conceptual question that it is group 1, and group 1 have 1 valence electrons. Once you remove the 1 valence electron from the fast ionization energy, second ionization energy would be what? Will be the core electron. This cannot be, because if you remove, this has 2 valence electron. Fast ionization energy is valence electron. Second ionization energy is the core. Still valence electron, and it's easier to remove that. So please remember that. Now, there's some irregularities you need to pay attention to, more so when you look at the orbital filling diagram when writing electron configuration. Recall there were 3 methods of writing electron configuration: the boxes and the arrows, where the arrows represent electrons. So the trend is not followed when added valence electron in the next element. Let's say here, you need to understand what this means. It's going to be an abstract unless you know what is going on with these elements right here, nitrogen and oxygen, what is going on here. These are just the Phelan shell in electron configuration. So if we have here, let's say oxygen, I'm gonna have let's start with nitrogen. Doesn't really matter which one, nitrogen, and then here is oxygen. All right, so oxygen, there is one S, there is two S, and there are three orbitals in 2p sublevel. So oxygen, see here, oxygen, all right, we should have here, let's move this. Oxygen, let's start with nitrogen. Nitrogen is number 7. So we would say 1, 2, 3, 4, 5, 6, 7. Remember Hans rule, when degenerate orbitals are occupied by electron, they are singly occupied first before you start pairing them up. So here for nitrogen, it's just a outermost sub-level being shown on the PowerPoint slide. Likewise for oxygen, this is 1s, 2s, 2p sub-level. Oxygen is number 8, so we have 8 electron and look at this, 1, 2, 3, 4, 5, 6, 7, 8. And what you see on the PowerPoint slide is just his outermost sub-level. 2s is sub-level, 2p is sub-level, and there are 3 orbitals in 2p sub-level. If you look at oxygen, there are pairing of electrons. So once we start pairing them up, there will be repulsion. Electrons tend to repel because of what? Because of negative and negative, they tend to repel. So here, they are not paired up. And if we were to talk about the ionization energy, if electron is repelling one another and we want to remove an electron, it makes sense that it will be much easier to remove that electron in a paired system. Therefore, fast electron to pair in one orbital also, electron repulsion lowers the energy. So here, I can say electron, let's look at that, electron repulsion. Electron repulsion lowers fast ionization energies like that. See that? So if you look at this system, or if given any other system, the best way to come to a conclusion which atom will have lower or greater ionization energies, to write down the electron configuration using orbital filling diagram. All right, here is an example on a question. All right, here is a question on repulsion. Why is it easier to remove electron or to remove a 2p electron from an oxygen atom than from a nitrogen atom? We talk about that. The correct answer here is C. Because of time, C explain more in details why 2p electrons removed from an oxygen atom is in fully occupied orbital will increase electron repulsion compared to 1O. So here, there is no repulsion. We have repulsion here, which will make it easier to remove an electron. Which one of the following correctly represent the third ionization energy of gallium? So there is the first ionization. This is first ionization. This is second ionization. We don't have anything. No, this is third ionization energy. Actually, C is the third ionization energy. We don't have anything like this. This is electron affinity. This is second ionization. This, there is nothing like this. All right, this is first ionization energy. This is electron affinity. Here the correct answer is C, third ionization energy. Oh, well, our dash have the lowest fast ionization energies of the groups listed. Again, this will call for recalling prior concept we learned before. And this is naming of the group. If you don't know which group is alkaline metals, transition metals, halogen, alkali, noble gases, you would not know. So fast ionization always group 1, which is alkali metals. Alkaline metals are group 2, halogens group 7, and the group A noble gases. This one will have the most or the highest fast ionization energy. Let's see, well, revisit the electron configuration. And writing the electron configuration for ions, we need to be able to write the electron configuration for neutral atoms, which was chapter 6 affair. This is something we learned in chapter 6. Please go back again and do the 1s2, 2s2, and so forth. When you generate ions, you remove electron in the outermost shell. For example, here lithium, okay, let me just minimize this. Lithium, if you look at the lithium, it's going to be 1s2, 2s1. But lithium, I positive, not positive 3, but I meant to say positive 1. We are less pi 1. This is con, and this is going to be 1s2. 1s2, and that is why we have this. Don't think that we are writing the electron configuration of just lithium, which is this is neutral lithium, but this is a cation. And remember, group 1, they will form positive 1, group 2, they'll form positive 2. So if I'm to write calcium, for example, look at this calcium, this will be 1s2, 2s2, 2p6, this is 10, 3s2 is 12, 3p6, and 4s2. Calcium cation, this will be 1s2, 2s2, 2p6, 3s2, and 3p6. So the 2 electrons are gone, the 2 electrons are gone. You may be wondering, for iron, this should be iron 2. This should be iron 2. By the way, iron is this ion. Electron configuration is 1s2, 2s2, 2p6, this is 10, 3s2, this is 12, 3p6, 18, 4s2, 20, 3p, 426, 3d6, 3d6. This is just for the neutral ion, for the neutral ion. However, for ion to ion, therefore, as the electron in the highest end or highest energy level are removed fast, which means this will be 1s2. Okay, this will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. No, but that's gone. This will be 3d6. The 4s2 is gone, so we remove this fast. You remove this, the highest n value electrons, remove fast, and then you go to the subsequent. You don't remove the outermost one, the D. No. That's how ions are generated. So for ion 3, Fe3, what is this? Is 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d5. I've removed the 2 electrons, and then I remove the 1 electron. I end up with that. Remember, we can also use the long form of electron configuration. This can be argon, which has 18 electrons, and then 4s2, 3d10, 3d6, sorry, 3d6, like that, 3d6 plus 2. This is going to be argon up to this point, and then 3d6, and then here is argon, just the short form, and 3d5 is the same thing. So just using the short form to write electron configuration for ion 3 and ion 2. There is no ion 1 place, no ion 1. So that's how you write electron configuration for cation. For anion, you just add electron. For example, fluorine, this is 1s2, 2s2, then 2p, what, 2p5. But negative, yeah, fluoride ion, this will be 1s2, 2s2, then 2p6. 2p6. You just have to add the electron. If it's negative 2, you add 2 electrons. Knowing the maximum number of electrons, we can go into each sub-level, So here is an example, 7.7 electron configuration for ions. Writing electron configuration for ions. Calcium, all right. Number 20 to 4s electrons are removed. And we have just like this is isoelectronic with argon. Cobalt, 3 electron. If you look at cobalt, let's see how this comes about. Cobalt is number 20, 26, 27. Number 27. Cobalt is number 27 here. So if it is 27, look at this. Cobalt, 1s2, 2s2, 2p6, 3s2, this is 12, 3p6, this is 18, 4s2, this is 20, 3d6, number 26. If we want to remove 3 electrons, cobalt 3 plus, these electrons right here will go away. All right, will go away this must have been cobalt to 3D 6. This is 20. Cobalt is 25, 24, 25, 26, 27. So this will be 1s2, 2s2, 2p6, all right, 2p6, 3s2, 3p6, and then this should be 3d5. This should be 3d5. If we are removing, unless this was cobalt to ion, this should have been cobalt 3 ions. Zone configuration D7. Yeah, this should have been D7 right here. 27. That's my fault. This should have been 27 right here, D7. So that we have here D1. We have here D6, number 27. So here we remove 2 electrons and 1 electron to create these for cations, to create that for cations. All right, so how you write, please pay attention for that. And for anions, you add electron. Remember, sulfur is number 16. If we add 2 electrons, gives us 8 electrons. And remember, we are using shorthand in this case. Write the electron configuration for chromium 3. Chromium is number 24. And if we do that, you expect this. This is just neutral chromium number 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. No, this is one of the anomalies. So 3d 424, 19, 3d5, 3d5. This is just neutral chromium. So if we remove 3, this will go, and the 2 will go from here, remain 3, and therefore Cr3 positive will be argon. I'm just going to abbreviate that for 18 electrons up to this point right here, 18 electrons, and 4 S1, 3D, not for S1, the S is gone for 1 electron, and then this is 3D3. Therefore, S is constant. For PR negative, this is just gonna be crypto number 36. It's just gonna be crypto number 36. Unless you want to PR alone is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5, 4p5 for just fluorine, but for this is going to be just krypton. You have extra electron for that. You have extra electron. Please, it's just repeating the electron configuration, which we looked at in chapter 6. This marks the end of part A. I'll come back again for part B for chapter 7. Continue reading chapter 7. All right, continue reading chapter 7. Do the online homework, My Love and Mastering. I recommend that you complete the homework assignment before taking the quiz, before taking the exam. Other than that, thank you. See you again.